Hello everyone, and welcome to our video on Greene's theorem. So let's start with the definition. So the positive orientation of a simple closed curve C refers to a single counterclockwise traversal of C. So if we look at this graph here, we've got this curve, we're going counterclockwise. We think of that as positive. And if we were going clockwise, we think of that as a negative orientation. So this should make some sense considering the standard orientation for the parameterization, let's try that one again, of the unit circle is x equals cosine of theta, y equals sine of theta, right? That's a counterclockwise parameterization. So it kind of makes sense to just make that our positive orientation. All right, now that's going to be important for this theorem, Greene's theorem, which is going to be a good friend of ours. Greene's theorem is a really useful tool for dealing with some line integrals that would otherwise be pretty complicated to evaluate. And the ability to use Greene's theorem to change these from line integrals into double integrals over regions is going to be super valuable, as I think we'll see in some of these examples. So Greene's theorem states, let C be a positive-oriented, piecewise smooth, simple, closed curve in the plane, and let D be the region bounded by C. If not it. Okay, well, there's a typo. If P and Q have continuous partial derivatives on an open region that contains D, then the line integral over C of P dx plus Q dy equals the double integral over D of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y, integrated with respect to A. So another notation for the positive-oriented boundary curve of D is this partial D notation. So we could rewrite this theorem in the same way, the double integral of dq dx minus dp dy dA equals the integral over the boundary of D of P dx plus Q dy. Another thing to look out for is that this version of the integral symbol, where you have a little circle through the middle of the integral, just means it's just a special notation to specify that your integral is oriented in a positive direction. So it still just means a line integral, but this specifies that it's oriented in the positive direction. Okay, so let's consider this example. Evaluate the line integral over C of x to the fourth dx plus xy dy, where C is the triangular curve consisting of the line segment from 0, 0 to 1, 0, from 1, 0 to 0, 1, and from 0, 1 to 0, 0. So let's just draw this curve out here. So our region D is the region inside here, and if we orient this in the positive direction, it should look like that. So what does Greene's theorem tell me I can do? It says, well, first of all, is your curve simple and closed? Yes, it doesn't intersect itself. It encloses a region. Okay, that's good. If P and Q have continuous partial derivatives on an open region that contains D, then these two things are equal. So if you take the partial derivatives of these two functions, you're going to get continuous functions, so that's all fine. So that tells us that if we wish to evaluate this line integral, we can make it a little bit easier by first calculating dq dx, which, okay, q is xy, so dq dx is just y, and dp dy, all right, well, p is x to the fourth, so the derivative with respect to y is just 0. So this line integral becomes the double integral, and I'll shorthand this. Or maybe I should just say p and q. Okay, so this is going to become the double integral of y minus 0 dA over the region D. But this is great because this region is one that we can pretty easily set up a double integral for. So this upper boundary here would be y equals negative x plus 1. So we can set this up as the integral for y from 0 to negative x plus 1 and x from negative 1 or 0. Oops. X from 0 to positive 1. So this becomes the double integral of y dy dx. And our inner bounds will be 0 to negative x plus 1. And then for x bounds, we'll get 0 to 1. So this is the integral from 0 to 1 of y squared over 2, where y is evaluated from 0 to negative x plus 1 dx. This gives me negative x plus 1 squared. Put the 1/2 out in front. Okay, multiply this out. We get x squared minus 2x plus 1. This is 1/2 times x cubed over 3 minus x squared plus x, evaluated from 0 to 1. Of course, when I evaluate at 0, I just get 0 here. So these cancel. Negative 1 and 1 cancel. So this is 1/2 times 1/3, which is 1/6. Now, just momentarily consider if we had tried to integrate this as a line integral. So we would have first had to have parameterized each of these lines, which are relatively easy, but that's still fairly complicated because we've got to parameterize these and we have to make sure they're parameterized in a counterclockwise direction. All right, and then we've got to integrate this integral 3 separate times, one for each portion of the curve. So in this case, being able to change to this double integral over the area, over the region, is much, much simpler in my view. Okay, so let's see what's next. Now, I do want to just put a little comment here. So I didn't include the proof for Greene's theorem. And if you're looking at just special cases of it, you can reduce this proof to something that is relatively straightforward. It's not super complicated or really hard to understand, but it is pretty long. And so I'm really just excluding this here for time. So it's definitely something worth looking at, taking a while to understand. It's valuable. It's not, again, it's not super complicated, but I'm going to exclude it here for time. Okay, so let's take a look at example 2 here. Evaluate the positive-oriented line integral of 3y minus e to the sine x dx plus 7x plus the square root of y to the fourth plus 1 dy. And another little typo there. There should be a little extra parentheses. All right. Where c is the circle, x squared plus y squared equals 9. Okay, so the first thing to do is to figure out what this region is going to look like here. So it's the circle with radius 3. Okay, so first we need to know, what does dq dx look like? That's just going to be 7. And what does dp dy look like? That's just going to be 3. Okay, and so what do we want to do then? Well, we want to integrate from we want to integrate dq dx minus dp dy over this region. So my line integral here is really going to be the double integral over the region of 7 minus 3 dA. Okay, so this seems pretty simple, but I do want to point out that in order to do this integral, we would need to write y as the square root of 9 minus x squared plus or minus, and we would have to split our bounds on our inner integral over these two functions. And so then when we go to integrate, we're going to pretty much be left with something that has to be integrated with trig substitution. So that would probably be a little bit messy and a little bit complicated. But what we could realize here is that not only can we apply Greene's theorem, but we can also change this to a double integral in polar coordinates. And that's going to really make things easier. So we would need to replace x and y in our function with r cosine of theta and r sine of theta respectively. But there is no x and y here, so we can just write 4 times. And now we replace dA with r dr d theta. So what is r? Well, r is just going to be, the radius is between 0 and 3, not 0 and 0. 0 and 3. And theta is just going to be between 0 and 2 pi. So this becomes the integral from 0 to 3 and 0 to 2 pi of 4r dr d theta. Okay, that's a much simpler integral than what we would have gotten. So this becomes 4r squared over 2, which is 2r squared, evaluated from 0 to 3, d theta. Now when we evaluate at 3, we're going to get 2 times 9, which is 18. And evaluating at 0 is obviously 0. So this is just 18. D theta gives me 18 times theta evaluated from 0 to 2 pi, which gives me 36 pi. Okay, so here we used Greene's theorem to turn this into a double integral over the region, and then we also used polar integration to make that double integral really, really easy to evaluate. So having these tools in your back pocket can really simplify a lot of these problems. Just taking a look at this, I think it should be pretty clear that these functions would be extremely difficult to deal with as line integral. And by putting it into this double integral form, using Greene's theorem, we just make our job a lot easier. Okay, so let's consider an interesting fact. Since the area of D is the double integral over D of 1dA, we can consider the problem of finding P and Q such that dq dx minus dp dy equals 1. Okay, so in other words, we're trying to set up the integral d1dA equals the double integral of dq dx minus dp dy. So the question is, what do q and x have to be? Well, they could be infinitely many options, but we can just consider a few simple cases. P could be 0 and q could be x. So then you'd get the derivative of q would be 1 minus 0 is 1. P could be negative y and q could be 0. So then you get 0 minus negative 1, which would become positive 1. Or you could get P is negative 1/2 y and Q is 1/2 x. And again, you take these derivatives, you'll get 1/2 plus 1/2 equals 1. So that gives us three possible line integrals that can evaluate the area of a region. So we could have the line integral, the positively oriented line integral of x dy, or negative the line integral of y dx, or 1/2 the line integral of x dy minus y dx. So this could give us a potentially simpler way to deal with evaluating various different areas of regions. So let's consider this one. Find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals 1, which again is like x over a squared plus y over b squared equals 1. So here we would get x over a equals cosine of theta. So x equals a times cosine of theta. And likewise, y equals b times sine of theta. So when we look at this, we can kind of think ahead here, right? Our area is going to be one of these line integrals. If I had x dy, I'd get like cosine and negative cosine. To have a cosine squared, I'd have to use a power reduction formula. And here, if I have x dy and minus y dx, I'm going to have some combination of sine squared and cosine squared. And the Pythagorean theorem might allow that to cancel nicely. So we're going to go with this version and see what happens. So a equals 1/2 the line integral x dy minus y dx. Now, in order to calculate this, I need my dx dt. That's going to be negative a sine of theta. And I need my dy dt. That's going to be b times cosine of theta. And so my area is going to be 1/2 this integral over c of x, which is a cosine of theta, times dy dt, which is b cosine of theta, minus y, which is b sine of theta, times dx dt, which is negative a sine of theta. All with respect to, I guess I've been writing dt, which is silly because I parameterize these with theta as my parameter. So I should call that dx d theta, dy d theta. And this integral should be with respect to theta. Okay, so let's rewrite this a little bit further. Now, I know that this integral is going to be from 0 to 2 pi based on the parameterization. And here I get ab times cosine squared of theta plus ab times sine squared of theta. And if I factor out the ab, I get ab over 2 times this integral from 0 to 2 pi of cosine squared of theta plus sine squared of theta, which is just 1. So this is ab over 2 times theta evaluated from 0 to 2 pi. But of course, that's just going to be 2 pi. That leaves me with ab times pi. All right. Well, that's it. That's the area enclosed by this ellipse. Okay, so far, what we've been dealing with are what are so-called simple regions. So these are type 1 or type 2 regions, as we've defined before. But Greene's theorem can be extended to non-simple regions as long as they can be represented as a finite union of simple regions. Okay, so this can seem a little bit messy at first, but I don't think it's too conceptually difficult. So consider D, the region that's the union of D1 and D2. So this whole thing is D, and D1 is this half, and D2 is this half. Then the boundary of D1 is equal to this C1 plus C3. So the curve that goes from here along the outside plus the curve along C3. And the boundary of region of D2 is equal to C2 unioned with negative C3. So here we've got D2, or C2 I should say, and then negative C3. Now we're specifying negative C3 here because in the orientation we've got C3 was originally going this direction, up, and C3, this is going the opposite of that, so it's negative C3. So we can apply on each of these regions Greene's theorem. And when we add them together, what do we get? Well, we get that the sum of the double integral over D1 and D2 is, of course, just the double integral over D. Now, the line integrals on the left is a little bit more complicated, but just notice that since we've got union C3 and union negative C3, those line integrals for these portions are going to be negative of each other, so they're going to cancel out. So here we'll just get the integral of the union C1 and C2 of p dx plus q dy. So in other words, even if your region is not a single simple region, if you can divide it up into two simple regions, then it's not a problem. Greene's theorem is still going to work. So let's take a look at this example here. Evaluate the line integral of y squared dx plus 3xy dy, where c is the boundary of the semi-annular region D in the upper half plane between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So it's very important that we pay attention to the fact that it says the upper half plane. And so this circle is radius 1, and the second circle is radius 2. So this, of course, is not a simple region, and we would have to break this thing up into multiple pieces, blah, blah, blah. We're going to end up looking at a way to get around that a little bit, but first, let's just notice, well, what does this tell us? Well, first of all, if I was going to try to integrate this line integral directly, I would have 4 different paths that I have to split up this line integral along, which could make things fairly complicated. On the other hand, we can apply Greene's theorem, and let's take a look at first dq dx. It's going to give us 3y, and dp dy, it's going to give us 2y. And so our integral can be written as the double integral over d of 3y minus 2y dA. Now, if we were to integrate this with respect to area, with respect to x and y, then yes, we'd have to split this thing up into 2 different regions in order to be able to break this up into simple regions that we can integrate over. But when I look at this, this looks like a really natural fit for a polar region. So I think to myself, well, I could always use r is between 1 and 2, and theta is between 0 and pi, and that's going to be a lot easier to deal with. So we replace y with r times sine of theta, and dA with r dr d theta. And so r will be from 1 to 2, and theta will be from 0 to pi. So this is the integral from 0 to pi of the integral from 1 to 2 of r squared sine of theta dr d theta. Okay, so that's r cubed over 3 sine of theta evaluated from 1 to 2 d theta. Okay, r cubed is going to be 8. So 8/3 minus 1/3, which is 7/3. Sine of theta d theta. Okay, the integral of sine of theta is going to be negative cosine of theta, evaluated from 0 to pi. This is negative 7/3 times negative 1 minus 1, which gives us 14/3. Okay, so now let's go ahead and consider a different issue that could arise. What if we have to deal with regions with holes? So consider our definition of orientation and imagine a person walking along a curve in the positive direction. In that case, they would be walking with the region on their left. So we think back to like this. Positively oriented, you're walking along your region. So if you imagine you're walking in this direction counterclockwise, then the region is actually on your left side. So when we deal, that was how we define this in terms of simple regions. But now if we have regions with holes, the inner region where the hole is going to be a little different. So we have to change how we think about this. So for the inner boundary of a region with a hole, we orient the positive curve clockwise. So on the exterior curve, counterclockwise is still positive. The domain D is on your left. But when you look on the inside, if you're walking along the inside curve, then if you want to keep D on your left, you have to be walking clockwise. Okay, so if we want to divide this into a region that we can work with, we could do that like this picture here. So we create a path from here to here and from here to here. And so we create a region that bypasses the hole here. And then down here, this region bypasses the hole. So then we get two regions that don't have any holes in them. And so, well, then what does that tell us? That tells us that Greene's theorem gives us the double integral of dq dx minus dp dy dA equals the sum of p dx plus q dy's integrals over both curves C1 and C2, right, C2 being the inner boundary. And that works because these boundaries that cross from the outer to inner are going to cancel each other out, right? They're oriented the opposite direction. And so when you sum these two up, we can just call this the integral of p dx plus q dy over C. So that would all seem fine, where C is the boundary of the whole region, but really C represents the sum of the two boundaries, the union of those boundaries. Okay, so let's consider this problem. So things become a little bit more complicated when you deal with a hole in the region. So if f of xy equals negative yi plus xj over x squared plus y squared, show that the line integral over C of f dot dr equals 2 pi for every positively oriented simple closed path that encloses the origin. Okay, so what does that mean? Well, you've got your origin, and you've got some simple closed path C. But we have a problem, which is that this function here is not defined at 0, 0. So there's a hole. Greene's theorem requires that the function, the vector field be defined everywhere. So there's this hole here, which adds a little bit of complication to the problem. So what we would like to do is essentially remove that problem. So how are we going to do it? Well, we could apply Greene's theorem if we had a sort of boundary between this simple outer curve and another curve enclosing the origin. Now what I'm going to do here is just, I could make this curve inside anything I want, but I'm going to pick something useful. So I'm going to make this a circle that I'm going to call C2. So maybe we'll call this other one C here. And so then you could divide this up in the usual way, right? You could have a path going to here and a path going to here, so forth and so on. And there's sort of two keys to consider here, which is that, yes, the integral of the sum of these two things is going to be equal to the integral of this vector field f over the region. Okay, so let me see if I can be super clear about what I mean by that. So what we're going to do here is we're going to use Greene's theorem to calculate this line integral, but we can't just do it directly because we have that hole in the origin that causes us we would not be able to apply Greene's theorem directly to the region if we included that hole in it. So instead, we're applying Greene's theorem to this region where we've got an arbitrarily small circle here, right? And of course, we can make this circle as small as we want, which tells us that, there's really no difference between the integral over this region and just excluding the hole itself. So here, our boundary for our region is really just C1 unioned with negative C2. So what we want to show is that the integral of f dr, well, we'd like to calculate the integral of f dr of C1, that's our original region, but instead we're going to look at the integral over C, where C is the union of C1 and C2. Now what we saw was when we have these holes, that's okay. Doesn't cause us a problem with Greene's theorem. We can still change this to the double integral of our dq dx dp dy. Now it might help here if I kind of rewrite f a little bit. So I'm going to write this as negative y over x squared plus y squared I plus x over x squared plus y squared j. So now I can calculate those derivatives a little easier. We'll do that off to the side here. So the partial derivative of q with respect to x. So we get the derivative of the top, that's 1 times the bottom, minus the top times the derivative of the bottom with respect to x, that's 2x, over x squared plus y squared squared. This gives me x squared minus 2x squared, so the top becomes y squared minus x squared over x squared plus y squared squared. And dp dy is going to be very similar. So we take the derivative of the top, that's negative 1 times the bottom, minus the top, which is negative y, times the derivative of the bottom, which will be 2y, over x squared plus y squared squared. That's going to give us what? That's going to give us negative x squared, negative y squared plus 2y squared. So that becomes, again, y squared minus x squared over x squared plus y squared squared. So what does this give us? This gives us dq dx. It's y squared minus x squared over x squared plus y squared squared minus y squared minus x squared over x squared plus y squared squared. dA. But of course, this is 0. So this is the double integral over d of 0, which is just 0. But again, here we found this is the value of this integral here. So that tells us that the integral of C1 f dot dr plus negative C2, the integral over negative C2 of f dot dr equals 0. But that implies that the integral over C1 is equal to negative the integral over negative C2 of f dr. But here, if we change the orientation of this curve, we could make this positive instead of negative. So this would be equal to the integral over C2 of f dot dr. Okay, so here's the benefit. See, we chose to make C2 a circle so that we could compute this second integral really nicely. That's really the goal here. So if we parameterize our second circle C2 as just x equals a times cosine of t and y equals a times sine of t, then dx dt is going to give us negative a sine of t, and dy dt is going to give us a times cosine of t. And so when I take the dot product of f and dr here, what should we get? Well, I'm going to try to skip a few steps here. I hope that's okay. So we're going to get the integral from 0 to 2 pi of, now we've got negative y, but this is, remember, we're taking the dot product with dr, so it's negative y over x squared plus y squared times dx dt. So that's negative y over x squared, which is a squared cosine squared of t, plus y squared, multiplied by the derivative with respect to x, or with respect to t of x. So that's negative a sine of t, plus, now here we've got xj, so we've got x, which is a cosine of t, times dy dt, it's a cosine of t again, over x squared plus y squared, so that's a cosine squared of t, plus a squared sine squared of t, these negatives cancel. So I get a squared sine squared of t plus a squared cosine squared of t. And if I factor an a squared out of the top and an a squared out of the bottom, those are all going to cancel. And I'm going to end up with the integral from 0 to 2 pi of sine squared of t plus cosine squared of t over the common denominator, which is cosine squared of t plus sine squared of t, dt, but both of those things are 1. So this is 0 to 2 pi of 1 dt, which is t evaluated from 0 to 2 pi, which is just 2 pi. So we did it. We did it. We showed that when this function is integrated over any positively oriented simple closed path that encloses the origin, you get that the integral over that path is 2 pi. So that's it for this section on Greene's theorem, and thank you for sticking around till the end. Have a great day.